Good morning, good afternoon, or good evening, wherever you are, and welcome to this keynote conference. Well, even though he's very well known for his contributions in the area of electric power systems, let me introduce you to Professor Vladimiro Miranda, who was born in Porto, Portugal. He graduated in electrical engineering in 1977 and received a PhD degree from the Faculty of Engineering of the University of Portugal in 1982. He joined this faculty in 1981. In 1985, joined ANESC, a top R&D institute in Portugal, where he was the coordinator of the area of power systems during the 90s. For 18 years, until June 2018, he was a member of the board of directors of ANESC Tech Portugal. Professor Miranda is an IEEE Fellow and member of the IEEE Distinguished Lecturer Program. As well, he has been responsible for many research projects at international level in Europe, United States, and Brazil, and has authored or co-authored over 200 publications, especially in areas related with power systems and the application of computational intelligence to power systems. Professor Miranda, it is an honor to have you here. The conference will be for 40 minutes. After 10 minutes will be a break in order to attend some questions, and then we will continue with the conference. And thank you very much, Professor Miranda, y gracias a todos los presentes. Thanks.
Hello, buenos días a todos. Un saludo especial para Uruguay. Good morning, everybody, or good afternoon, I don't know, or good evening, who knows. I am honored to be here I'm grateful to the conference organization. I wish them well. I know that these are difficult circumstances to operate a conference, but conference is nothing compared to your health. So, first of all, before I start my speech, please keep safe. Then I'll just explain that I'm going to talk to you about something interesting, I believe, but I will do a break in the middle. Around 20 minutes after I start talking, I'll do a break. So to allow you to ask some questions, and Claudio will moderate that, I hope. And then, so you can ask some questions. I will interrupt. Eventually, some of you who may be sleeping from my speech will wake up and pick up the rest of the conference. So I'm going to share my screen and start my talk. Wait. Screen. I think this is. I think there it is. I suppose you are seeing now my opening slide. Okay, believing, yes. The thing is that I don't think, I'm sorry. Is this the one? No, it's not. I'm sorry. Just a moment. It's this. Okay, wrong conference. I'm in the middle of several conferences, so this is the right conference. I'm talking to you about something which is trending now, parallel processing revisited. And the thing is that parallel processing was in some way...
Excuse me, Vladimiro, it seems that no se ve la pantalla, parece, la presentación.
No se ve?
Okay.
Okay, let me try again and see what's going on. Let's see what's going on. Wait a minute, please. What about now?
Excellent.
So it's not this one. Wait a minute. this one. Okay. So, as I was saying, parallel processing, I'm sorry that you were not seeing the screen, so now it seems it's good. Parallel processing it was something that was promised years ago that would be a nice solution for computing. And several experiments were done in terms of grid computing. Of course, I'm talking about power system applications. There are many other applications. But it is an old dream, and it deviates from the old paradigm of von Neumann about the series processing concept. The acceleration of computing relied mostly on faster clock frequencies, and this met physical limits. So the other attempt was to try and split algorithm into independent chunks, or called threads, that could be processed at the same time and in parallel. And this was met with limits also, being the most important, the non-parallelizable parts, communications and tasks before parallelization may come to dominate the computing time, so it met also the difficulties. For the power industry, parallel processing was never a real success because of costs of specific hardware or the need for special languages. I remember the times where people would call about a cubic architecture of parallel processing, etc. Need to have specialized programmers in unique languages and dependence of unique skills you would not find in the market applications addressing parallel computing, etc., etc. So the success in adoption of parallel computing was very small. There's many ways that we can address the parallel computing, and we will be especially talking about two of them. But let's say that the most importantly tried in power systems were the cluster computing or grid computing, where computers communicate over the internet. So we may have several computers at the same, even spread out, and they communicate over some Ethernet infrastructure or something like that. And recently, we have the emergence of graphics processing units, GPUs. They were originally developed and optimized for processing computer graphics and associative massive data parallel operations. But in recent years, they started being directed to general purpose computing. So NVIDIA even coined the term GPU, that would be general purpose graphics processing unit. The grid computing was the strongest attempt that I know of trying to build parallel schemes that would be workable in the industrial framework. And I will give you examples that delivered, that promised a lot, but then by one reason or another were not very successful in having this spread out in the industry environment. One of the best or easiest ways of thinking about parallel computing is when adopting intelligent agents. Intelligent agent is an autonomous program that responds to the environment or initiates tasks according to goals that it has embedded. And one of the standardization of intelligent agents was the FIPA, a standards organization that was in 2005 recognized by the IEEE Computer Society as a standards community. And they developed standards and recognized FIPA compliant technologies, embedding FIPA specifications, and this allowed it a programming environment that would be replicable. One example of such environment is Jade, the Java Agent Development Framework, is a platform for development of multi-agent systems that supports communication among agents and provides a standard implementation. The origins of FIPA were originally located at Telecom Italia, and Leonardo Chiariglione was a great promoter of these standards. So I have an example to you of parallel processing using a platform of 19 agents for a model to simulate the retail market, energy retail market. And you see here the representation of agents in a market where electricity, gas, and heat are competing, heat under the form of steam or whatever. They are competing for consumers, for market shares, etc. So all these agents, 5 retailer agents, 3 delivery agents, 3 regulators for each market, an economy environment, commercial consumers, consider an agent considering consumers as a group, commercial, residential, industrial, and 3 market operators. All this in a platform that could be put in parallel using grid computing with 5 PCs connected through a local area network, and the agents were located in different PCs, as you see in the figure. The communication, there was a communication burden of writing and reading from the Blackboard agent, which was an agent that would publish all the information that must be public and known by all the agents, and also information that agents are obliged by regulations to make public. So there was some communication burden. Nevertheless, we learned some lessons from this platform. One interesting thing in a 2-year daily simulation in a system, we compared weak regulation against strong regulation, and the conclusions were amazing in the sense of emerging behavior of agents. When we had weak regulation, so weak consumer awareness, low reaction capacity of the consumers, and the companies were reacting much faster to the moves of the competitors than consumer reaction. Then what we saw was that without any programmed intention, agents found out that there was in their interest to have collusion. So prices went steadily up, and the market shares kept basically the same along the simulation. No change in market shares, but prices going up, so the consumers lost. When we increased the strength of regulation, for the same time period simulation, we discovered then that the prices oscillate quite a bit, and the market competition was real. So market shares changed according to consumer preferences, according to the strategies of the different competitors to offer conditions. Now, prices oscillated in the situation where there was more control on prices. When there was no control on prices, the prices just grew steadily, because you don't need to write a contract to have collusion. You just need to watch what your neighbor is doing to have an actual collusion. So this led, in fact, to our studies on the efficiency of parallel computing. And we came, after optimizing all the system, we came to a speed up of 10 times with that process when compared with the same simulation but running in series in a single computer. So 10 times was the best acceleration factor that we reached. And I have another example here, which is using parallel computing for sequential Monte Carlo. Monte Carlo is a very heavy algorithm, everybody knows, and sequential Monte Carlo is still even heavier. There is an obvious possibility of using parallel processing, because after you sample a lot of states, you can analyze each state in parallel in principle. That's not exactly correct with sequential Monte Carlo, because what happens in one state depends on what has happened in the previous time moment. So it is a bit tricky. So in parallel processing, there is this difference to sequential simulation, because we have in chronological Monte Carlo, we must produce sequences of events, then have state evaluators, and then an index calculator. We implement the parallel version using the Jade library also, and we had a different architecture, which was a synchronized approach, where agents would deal with buffers of sequences, so that the state evaluator would have actions synchronized. I wouldn't want to enter in many details about this, but the speed-ups we got with the grid computing were again between 10 and 13 times for networks like including the Brazilian Southeast system with 242 generators and the network, and we simulating 2,500 years for reliability calculations, and we got a speed up of 13.5. So not so far away from what we had with the parallel agent platform for the market simulation. Okay, so this is the let's say our experience in terms of having parallel processing using grid computing. And why using grid computing? One of the objectives was the following: we wouldn't need to have very special dedicated hardware with very costly specifically for that kind of applications that would impose costs to companies and specialized people to deal with that, etc. So let's use the computers that exists. Let's use the connectivity that is there in place and try to put up parallel process. 10 times is interesting, but is it a game changer? Maybe not. So I'm ready now to talk to you after the promise that was not delivered. I can talk to you now about the return of Jedi with the lightsaber, with the graphic processing unit. But I'll make a pause here to see if there are some questions that you would like me to answer, and maybe to rest a little bit from my presentation. And I will continue talking about the advancement with the graphic processing units. Are there any questions?
Yes, there are some questions. The first question is, from your viewpoint, do you think that parallel processing could allow real-time stochastic studies to improve the way in which electricity markets are working or operate?
My answer is clearly yes, but not with these approaches that I have been talking. So please stay to the second part of my presentation, because yes, that's what we are working now. We are showing that we can bring this to real time and to operating conditions. Notice that the projects that the applications that I talked to you about were directed to planning.
Okay.
Time-consuming applications, but that is not the most let's say important application of parallel processing in my view. To have it industrial significance, We must find a niche in the operation environment.
Okay, because the other two questions are related as well with the operation of power systems. And there is another one, is how parallel processing could improve the selective transfer of information between different companies. Companies don't want to share all the information, but in an operation, perhaps, I don't know, how they can transfer information.
Well, the transfer of information is important in many cases. The thing is security and what information is transferred. And it is not really connected with parallel processing, in my view. But I'll give you an example where information is needed. In the interface between transmission system operators and distribution system operators, they need to exchange information, namely so that the transmission system operator can suggest changing the operating points at interface substations to run the network in a more secure manner. So they need to exchange information, but that is related to two things: is the protocol of the data exchange, and also on the models we can develop to pass information and guess what is happening on the other side without receiving direct information from the other side. And this happens right now. I can tell you that in Europe, we already tested with EDF and from France and EDP from Portugal. We tested already models for the negotiation between transmission system operators and distribution system operators to define policies at the interface. So this is possible. But parallel processing, what will it help? These negotiations, in some cases, must be almost real time. Okay. And so, in order to tackle with the large volume of the large dimension of the problem, you need to speed up your calculations. You can no longer rely on algorithms thought for planning, and this is where parallel processing may play a role.
Okay, so the other questions are about the operating of power systems. So if you want to continue.
Okay, I'll continue then.
Thank you.
Let me see if I don't make another mistake in sharing the screen. This will be this one. Share. Yeah. Okay, I think, Claudio, this is okay. You are seeing again my lightsaber?
Yes, it's okay.
Very well.
Thank you.
Okay. Now, in the parallel universe, it's sort of a joke, in the parallel universe, a new star is born, which is the graphics processing unit. And the GPU was developed to satisfy the requirements of computer graphics processing, including heavy matrix algebra in massive ways and with independent simultaneous threads. How you process the image in one corner of the graphic display is independent of how you process in the other corner, etc. So there was this possibility, which actually brought real motion to graphics. This possibility was satisfied with the graphics processing unit that equips many computers that we have around in the world now. And as I said, NVIDIA proposed the GPU concept, and even we were involved with NVIDIA in some early experiments to demonstrate that scientific calculations could be done using this architecture that was developed for the control of displays in graphic displays in computers. So you have an application code that can be parallelized in parts and dealt with by the GPU, and then you have a rest of sequential code. What is the difference? We are not not talking about 5, 15 parallel things. We are talking about thousands, tens of thousands, or even more, of parallel threads. Does this make a difference? Yes, yes. So there are several developments of graphic processing and platforms, and the tendency is to develop libraries and platforms that can be used at high level by languages that are already known by programmers. Say the one developed by NVIDIA supported a compiler for Python, and so the difficulty in learning how to program something is severely reduced, considerably reduced, because you don't need to learn a special language to program, etc. You just need to learn some specificities. And these platforms that have from different manufacturers, but basically those are the most important ones, are there listed in my screen, led to a minimum of effort. I can tell you that my power system students at my university, in 3 months, that they write programs and satisfy the requirements for their master degree thesis in GPUs, and we are talking about power system applied programs, so it's a negligible time. Now, the thing is that in the age of parallel processing, the oldest machine is our brain. This is massive parallel processing. No wonder that some neural networks that in structure are also parallel structures, are mimicking our brain, were developed following the example of our brain and the so-called convolutional neural networks. Are an example of the inspiration of the connection between the visual cortex and the hippocampus in our brain. You see in the figure the neural network, as best as we know today, of the human brain, connection of the hippocampus, the visual cortex below with the hippocampus above. But this neural network, in fact, has a sort of a shape or architecture as a tapered network, larger at the base, and the output is narrow. And this is, and it is divided in chunks. The information is not fully processed at the same time. So this structure inspired convolutional neural networks to process images for image processing. So you have neural networks that operate by, the input is not a vector, is a matrix, is an image. The image is divided in several blocks, and each blocks are processed and condensed until we have a recognition at the end. And this structure, because it has independent blocks being dealt with, allowed GPUs to train convolutional neural networks. Everybody knows in the past saying, oh, training neural networks is very time consuming. No longer. This is the problem. I'll give you this example. We installed in South America, Brazil, Argentina, Chile, but I'll focus on Brazil. We installed a lot of PMUs around the country, connecting in low voltage and collecting information on the power system, and these informations were all relayed to an observatory in the city of Florianopolis. And we could collect examples, like I'm showing you here, examples of, this is frequency. The many events collected, they were all referred to the beginning of the event, many events on generator tripping, on line tripping, on load sharing, or on oscillations in a DC link. And all these events we have a very big database, many years of data, so we could work with these events, treat these time events as images, and you see here 4 images reproducing the events. The way we converted a time domain event into an image is for another talk, but beginning with these images, we input these images in a convolutional neural network. We tried different sizes of images, never mind, just treat the time information as images, like in our brain, and we got this structure of convolutional neural network, and finally, we got 100% classification, good result, 0% errors with the 30 for 40 pixels image of dynamic events. Now, what is relevant for our talk is that we could train the neural networks with the GPU. And this reduces the training time to 16 seconds. 16 seconds is compatible with the operation domain. So if you need to retrain a neural network because there are new data coming, etc., the training time will be woof. So this forms the core of an adaptive recognition process that can be in an intelligent local agent. And it is compatible with the operation environment. The speed up from training with the CPU series machine to GPU was about 30 times in this case. So it's a considerable speed up from 7.5 minutes to 16 seconds. This is amazing. But I will give you another same kind of example. We did it with for the distribution environment to recognize the status of breakers. So only based on data, information arriving on voltages or power flows around the network, and we would recognize how is a breaker open or closed. So I'm not going through the details, but we could discriminate and build an image of the network conditions. Here are examples of breakers. When the breaker is closed, are the images on the left. When the breaker is open, are the images on the right. And using a GPU, we could process this extremely fast and got success rates of about 100% of recognizing if the breaker is open or closed when you have no signal coming from the breaker and no signal coming from the line where the breaker is. So only signals around, but you lost any information or it is failed or whatever, and you still have. And the GPU training made this, again, 30 to 40 times faster. But I will go to even more impressive thing, which is sequential Monte Carlo on steroids with the GPU. Sequential Monte Carlo is a very difficult process. In 2008, we developed a model that has been continuously developed since then to Red Eléctrica of Spain and EDP of Portugal to simulate the whole Iberia Peninsula, so Portugal and Spain, maybe a peak of around 70 gigawatts. Portugal and Spain together simulate the security of supply until 2025. That was it. And we had to do it because of the high penetration of renewables in Portugal and Spain, as you know. We had to, the people were afraid what's going to happen, so we built under contract for them. We built a sequential Monte Carlo. In some cases, it would take 11 hours to do one simulation. Now, what we did was, let's put sequential Monte Carlo inside the GPU. And so we developed two strategies to develop this programming, depending on if the states are very heavy to analyze or not so heavy to analyze. We used this GPU, this NVIDIA GeForce that you see there. The sequential Monte Carlo was done by fixed hour intervals, And here are the results of two tests with the IEEE reliability test systems of 79 and 96 buses, and transformed reliability test systems for including high penetration of renewables. And you can see the difference. We got accelerations of almost 300 times, 250 to 300 times in the calculation. So instead of having 5 or 7 hours of calculation, we have only 95 seconds or 89 seconds of calculation for one of the strategies, which is absolutely amazing in speed up. For instance, with the 96 bus test systems, we got the same kind of speed ups. These gains, and notice, these gains were obtained without any convergence acceleration technique. We got even faster speed ups when we applied importance sampling, when we applied other techniques that would go even faster on this. But this kind of speed up brings Monte Carlo into the operation domain. And this is very important when you integrate renewables, because there is the evaluation of risks and including the tails of distributions still today requires Monte Carlo and special techniques to evaluate that. And up to today, you could not do this in real time in the operation environment. But if you have a process that takes 1.5 minutes, it is compatible with decisions that take into account risk at operation level. So this is a game changer. Now, this is my vision for the future. The problems are becoming wider and dynamic. Because you have a bigger problem and the dynamic, so in steps in time, the matrices describing the problem are becoming sparser and sparser and prone to be dealt with parallel processing. The real-time dynamic security system is moving from a wish to a real need in the operation. And parallelized models can give an answer for the operation domain to have precise and accurate dynamic evaluations of the system, not only the classical static evaluations. Then we have renewables. And when you need with the renewables and uncertainty about renewables, you need to deal with many scenarios in the future. Wind power forecasting relies today not on point forecasting, but on uncertainty forecasting. And there is even ramp forecasting. And you have to test for many scenarios. You need techniques that can do very fast assessment of what's going on. And so again, you need that at the operation level, so parallel processing is a need. And the solutions implemented in graphics processing units may bring the algorithms to the operation domain, algorithms that in the past could only be applied in the planning domain. I see a technological transformation. I believe that GPUs will provide a technological support for the changing paradigm. I can see local agents based on a GPU to process very fast many things and communicate information in the operation domain. I can see that solution providers to companies can now, instead of supplying a software, they will deliver a GPU with the software inside. And this will change many processing environments and many computing environments in the power industry. And also, I see that to enable this, we need to change a bit the education and research at universities and research institutions to train engineers to live with parallel processing, because today most power engineers are not really trained to live in a parallel processing environment, and to train researchers and developers to deal with and provide information supported on GPUs and processing technology. And this, the capacity of GPUs will allow local intelligence to exist, fast recognition of events, and parallel processing will be perhaps a change in paradigm. So thank you very much. And this is what I was ready to tell you today.
Okay, thank you, Vladimiro. There are 3 questions. Some of these questions are related to the control centers. The first one is, do you know if there are energy management systems that are implementing parallel techniques in their suites of programs?
I'm not aware of that in general terms, really. I'm not aware. We are working on that, but I'm not aware that it is, let's say, commercially available.
Okay.
And I believe that it will not be a one-off solution. I believe that you will start by introducing GPUs in some applications, and then they will multiply. Because at some levels, you don't feel the need to have this fast processing because you already have some processing. But I'll tell you one example where you will see the need. Okay. State estimation is for some decades stagnated in an old paradigm. But in fact, now
this is the other question. Eh?
Really? Okay. Yes. Please go ahead with the question.
Could be used in real-time state estimation.
Yes. Why do you need that? Because from these informations of every 1 or 2 minutes that in tradition we would have, we see now PMUs going around. And PMUs, give you a rate of information that was not admissible by the old algorithms and programs. What happened? People installed PMUs and then dealt with the PMU information as if it were exactly the old information, injecting it in the old programs. Why do you do such an investment to use the old technology again? PMUs offer you such an amount of information that they lead to dynamic information on behavior of the system. However, you cannot process that information in the old-fashioned manner. If you have one vector of data arriving every 20 milliseconds, or maybe it's faster in Brazil or United States. In Europe, it's 20 milliseconds. You have to process that very fast, and it's not only processing data, it's diagnosis, recognizing events, thinking about, so lots of things have to go around. So you will need parallel processing to deal with this in real time, and the only way I can see with modern technology is GPUs applied to parallel processing. We have been working on that as well. And there's a couple of very interesting results that we achieved, including applying different things to evaluate the quality of the data coming, and applying Bayesian inference to deal with the time sequenced information that come with the PMUs, and to deal with something else. There's an IEEE paper coming up very soon, to deal with systems that have now three levels of sensors in different time frames. Okay. You have the PMUs very fast, you have the classical devices, say 1 minute,
SCADA devices.
And you have the smart meters. That is at 10 minutes, every 10 minutes. And all these have information, but they must be fused together. So you must work at different layers, and these layers must interact. We have achieved very remarkable results. Maybe in the coming conference I can tell you about that. Okay. But my answer for that interesting question, which means that people are, look, Claudio and audience, the question is so interesting because it shows how this worries people in the industry and in the operation domain. People know that they are flooded with a tsunami of data. Yeah. And they don't have the tools to deal with that. There are two kinds of tools we need: intelligent tools and very fast computing. We need both. Okay. So this is my answer.
Okay, there is another answer relating to another question relating to your answer. Parallel processing could be used for automatic reconnection in case of faults. I mean, I think that should be even detect and so on. Well, please.
Yes. Actually, one of the topics that I touched lightly, and I ask your forgiveness because many subjects I could digress and go deeper in the subjects. I just touched lightly because I was addressing parallel processing and not the details of the techniques. Mm-hmm. But one of the techniques I told you about was about detecting breakers that are open or closed, but this can happen as a sequence of an event in the network, a disconnection, something like that. And you need very fast recognition of what happened and self-healing going after that, automatic reconfiguration, etc. You need that. But you need something else also, and the parallel processing comes again in this. You need to have models that recognize also the injection of malicious signals. Cyber attacks will be real. The more and more we rely on internet-like connections and communications and distributed intelligence in the system, you'll be more prone to cyber attacks. And also this parallel processing is needed to have agents aware of the situation and react.
Well, this is relating with the last question. When making decisions based on PMU measurements, how do you assure that the accuracy of these measurements? I mean, you are doing, okay.
We know today how to deal in a large extent with accuracy and gross errors coming from some failed device. Mm-hmm. We have even developed a solution that deals with that information and can, in many cases, can tell the operator there is a wrong information and the an unexpected information, mm-hmm. surprise effect, something that is not matching here. But this we can distinguish now if this comes from a sudden event that happened in the network, a disconnection, or a sensor that failed. Okay? So a failed sensor in the classical system may be similar to a disconnection in the network, right? Now we have the means to say, because of the PMU information and the models we built, we have the means to say, in many cases, this sudden jump in data is due to systemic failure or due to communications or sensor failure. And this is also important for the cyber security, because if you inject a malicious signal, it is like a sensor failure. It's not like a systemic failure. Yeah. It would be much more complex to inject a number of signals to simulate a systemic failure. So at the same time, we are also moving in that direction. We already have solutions for that, and I thank you for the question.
Okay, so, well, that's all, Vladimiro. So, just many thanks for your conference. Many thanks for attending this session. And well, enjoy the conference, and we will keep in touch.
Thank you very much. I hope everybody stay well, take the pandemic seriously, but live life to the full extent. Thank you very much.
Okay, muchas gracias y saludos
a todos. Gracias a todos. Un abrazo para todos los uruguayos.